Hello, we are Sara and Allan, and today we are going to present our final project that is solving a definite integral with Fortran 19 program using the Monte Carlo method for integration. Our contents are divided in objectives, introduction, code highlights, results, analysis, conclusion, and reference. The Monte Carlo method uses randomness to solve deterministic problems. This means that results are computed based on the repeated random sampling and statistical analysis. This method allows modeling complex situations with many random variables. It is rarely used in physics, such as statistical physics and thermodynamics. Can also be found in game theory and in finance. It was developed by studying Allan for the Manhattan Project.
Our main objectives are to write the code with Fortran 90 for a program that can numerically solve an integral using the Monte Carlo method. We want to generate a list of random numbers, use the code to obtain the results of two known functions, analyze its error, and compare this method with another integration method in one dimension, such as Gauss 1D. Now we're going to talk about random variables, whose values depend on the outcome of a random phenomenon. We will obtain them by using the linear congruential generator, which is an algorithm that uses formulas to produce sequences of random numbers and is defined as equation 1. A and M are constants determined by the user, in this case ourselves.
The Monte Carlo method is based on two principal theorems. The first one is the law of large numbers. That is a theorem that describes the result of performing the same experiment a large number of times, and the average of all the trials should be close to the expected value. The second one is the central limit theorem, that says that the normalized addition of independent random variables tends toward a normal distribution. There are two ways to represent the average value of the function, as we can notice in equations 2 and 3. And therefore we can write the estimate value of the integral as in equation 4, where each xi corresponds to a random value between the interval a and b. Then this function is to be evaluated in the different random numbers, and then sum them and multiply it by the quantity b minus a over n, and that will correspond to the integral value. To compute correctly the errors, first we need to have a set of values of the integral. This means that we need to realize the process several times. The variance is going to be given by equation 5 and the standard deviation by equation 8, and this is going to decrease as 1 over the square root of n. This means that we need to have several trials in order to minimize the error. For our Monte Carlo method, we compute two main subroutines. The first one related to the main integration part, and the second one related to the generation of random numbers. The Monte Carlo one, as an input, we have the interval, the amount of random numbers, and the repetition times. Our output is the integral value. Highlight, we need a vector to save the random numbers and to evaluate them in the function. As we are repeating the process several times, we need to put everything into a do, and then multiply and divide by other terms.
An interesting subroutine in our code was the one that generated the random numbers. We used equation 1 to generate the sequences of numbers, and with each run, we changed the value of p by adding 0.01 so that the list of numbers was different in each run.
To prove the Monte Carlo method, we wanted to evaluate two known functions. The first one, x squared in the interval 0 to 1, and the second one, sin of x in the interval 0 to pi. For both cases, we evaluated 150 random numbers and 300 random numbers and repeated the process 10 times. For the first case, we noticed that the closest value to the expected one is with 300 random numbers. So we expected that if we use more random numbers, then the value of the integral is going to be close to the expected one. But this did not happen in the second case. In this case, we obtained that the closest value to the expected one was with only 150 random numbers. Therefore, we perform an analysis of the distribution of the random numbers and of the value of the integrals.
We wanted to analyze the errors of each integral value with respect of the known theoretical value. So the problem was run several times by reading parameters so that the most efficient combination could be found. The first analysis was performed by obtaining the value of the integral of x squared in the interval 0 to 1, and the second analysis was made by obtaining the value of the integral of sin of x in the interval 0 to pi. The known values are 1/3 and 2 respectively. The first analysis for x squared was performed by establishing the number of times the program was run to 100, 200, and 500, and varying the amount of random numbers generated per run. Looking at the graph, it's clear that the sample that showed the lowest relative error was the one that was run 100 times compared to the ones run 200 and 500 times.
In order to analyze the distribution, a new code was written, and the aim of the program was to perform a statistical analysis by obtaining the measure of central tendency, mean, median, and mode, and also the class size. For the random numbers, we took an arbitrary generated tables of 150 numbers, and then the following histogram was constructed. As one can see, these do not follow exactly a normal distribution, so this might have an impact in the final result of the integral. From the integral values, we took the case of x squared in the interval 0 to 1, and also we consider 150 random numbers, and the process was made 15 times. They also do not follow a normal distribution, but seems to follow the distribution of the randomly numbers.
The second analysis of x squared was completed by establishing the amount of randomly generated numbers per run to 100, 200, and 500, and varying the amount of times the program was run. By looking at the figure, we can say that all three variations show a minimum value of the error with the program run in the interval between 77 and 100 times. On the other hand, the first analysis for sin of x was performed by establishing the number of times the program was run to 100, 200, and 500, and we varied the amount of random numbers generated. By looking at the graph, it is clear that when running the program 200 times, the relative error was at its lowest value compared with running the program 100 times and 500 times. The second analysis of sin of x was made by establishing the amount of randomly generated numbers per run to 100, 200, and 500, and varying the amount of times that the program was run. All three variations of the value of the amount of randomly generated numbers showed a minimum value of the relative error when the program was run 300 times. So we can say that the program doesn't need to perform at full capacity for obtaining an approximate integral value. We also can say that the amount of times the program was run showed to have a direct impact in the relative error of the result, while the quantity of random numbers generated didn't have a huge influence in the relative error of the final result.
For the analysis in the first case, we noticed that the minimum value was obtained using 300 random numbers and 10 times per the repetition, and is this one. After doing the error analysis, it appears that the best approximation for this integral is obtaining using 100 random numbers and repeating the process also 100 times. With this, we only obtain our percentage error, or 0.18%. In the second case, we did exactly the same, just that the closest value was presented with less random numbers, and then after doing the error analysis, we obtained that the best result will be obtaining using 300 random numbers and repeating the process 200 times. With this, the percentage error was 6.05%. This value is still really far away from our expected value in contrast with the other one. Just for the sake of curiosity, we wanted to perform a contrast with another integral method. In this case, we chose Gaussian in one dimension, and after performing the both known functions, we noticed that this result has a better approximation than the Monte Carlo one. Conclusions. The Monte Carlo method is not a great method, and in general, its converse is independent of the dimension. This is why one can have a good solution approximation. For a better code optimization, it would be better to set an error tolerance with respect to the variance or absolute error. The developed program needs to be run between 100 and 300 times to minimize the relative error. The quantity of the randomly generated numbers evaluated do not have an impact in the relative error. Gauss in one dimension gives a better approximation than the Monte Carlo method, using less iteration and thus less computer resources.